Hey, welcome to chapter 12. It's the last chapter, and I'm trying a little bit of new technology today. The downside is I have no idea if it's actually recording the camera, but the plus side is that I should be able to draw on the screen, and whether it's going to be helpful or not, we'll see about that. But chapter 12 is about the human body, and this is a subject that it would be easy to talk about for the whole semester, you know, if we wanted to take an anatomy class or a physiology class. And it's fun too because it's a subject that everybody's interested in typically because, hey, everybody has a body and, you know, they have their own study guide. You can look at your own body. Now, what you cannot look at too easily on your own body is cells. You can take a scraping of your cheek cells. For instance, take a toothpick and scrape the inside of your cheek and make a little microscope slide. You might have to stain it. But it won't look like a whole bunch. You know, you'll get some picture that looks like this. You'll see these little tiny cells under the microscope kind of scattered apart, maybe broken up. And you'll see little dark spots, the nucleus of the cell. And frankly, the ones in your cheek are probably not alive. But you are made of trillions of cells. And I said yesterday that, or the day before, you're actually more bacterial cells than you are human cells. That's true, but the bacterial cells are teensy tiny. So here are a bunch of bacterial cells on one of your cheek cells, these little tiny dots here. So there are many more bacterial cells than there are human cells in your body. Another function for that is that in your intestines, these bacterial cells are really packed in, and your cells are just not that tight together. There's a little more space between your cells. Now, technically, you could say, well, bacteria in my intestine, you know, that's not really in my body because this is just a tube going through me, right, from mouth to anus. And my body is this stuff, you know, this stuff all around the tube. This is me. And my body is all these cells, and I'm just a carrier of all the bacteria that are in my intestine. That's fine if you want to think of it that way. Okay, actually moving on to the topic at hand though. Cells, that's the functioning unit of living things. You have to have at least one cell to be alive, and you can have many, many cells packed together like a human or a dog or a tree or an elephant. Cells get organized into tissues where it's a whole bunch of cells doing the same thing, working together. So a whole bunch of muscle cells working side by side would be muscle tissue. Now, most of the time you have multiple tissues all together, and when you have multiple tissues together, it's going to become an organ. So maybe here are a bunch of muscle cells, and so this is muscle tissue. But your muscle itself isn't going to have just muscle tissue. You're going to have maybe some nervous tissue going there. You're going to have epithelial tissue covering it. You know, the whole muscle will be bound together with some sort of epithelial tissue. You'll have blood vessels going there, which has connective tissues. And so you'll have more than just one tissue type working together. And in that case, it becomes an organ. So groups of different tissues working together for a common purpose, that would be an organ. You have four main groups of tissues: muscle, connective, nervous tissue, and epithelial tissue. Muscle tissue is pretty simple to understand. It's what moves your body, and so these are cells that can contract. And muscle cells are very large in terms of cells, especially very long. So your biceps muscle, here's somebody's arm here, okay, and they have this, they got a big biceps. Woo. Okay, that's supposed to be an arm, by the way. Here, there's a neck and a head with a tiny little head. Okay, as you can see, drawing on this isn't so easy. But for a biceps muscle, the cells each go the length of the whole muscle, and there are many, many cells that make up this muscle, and they work together in groups, but each cell is the length of the entire muscle. That's really huge for a cell, And if you zoom in on it, what you actually see is that the cell once was a whole bunch of different cells, and now they've been put together into one giant cell. And it's considered one giant cell because it has one cell membrane around the whole thing. But you can see it actually has multiple nuclei within it, and it used to be hundreds and hundreds of cells lined up, but they're all joined together now into one big cell. So that's how muscle cells get to be so big. They're also quite wide for a cell because they have so many muscle fibers, little microscopic structures of muscles in them. Okay, we'll talk more about muscles in a minute. Connective tissue, holding things together. So how are you going to connect this muscle to the bone? Well, there's going to be a tendon. There's going to be a tendon there. There's going to be a tendon here that comes down just onto your forearm. You can actually, when you tense your muscles, contract your muscles, you can often feel the tendons at the end of the muscles. Behind your knee, tense the hamstring muscles in your thigh. So the back of the leg, tense those muscles, and you can feel big, thick tendons in the back of your knee. So that's connective tissue tying the muscles to the bones. Those are tendons. Ligaments that connect bone to bone, that's connective tissue. And then there are things that are connective tissue that don't really seem like they're connecting things, but they're still considered connective tissue. Fat is considered a connective tissue. So you can argue, well, I've got a little layer of fat beneath my skin, and it's connecting my skin to my muscles. So it is connective tissue. Blood doesn't seem like a connective tissue, and it's certainly not solid. It's a liquid connective tissue, but blood is actually a connective tissue. And cartilage, like in your nose or in your ear, or at the ends of your bones in your joints, there's cartilage. That's also connective tissue. What about the bones themselves? Yes, also considered a connective tissue. So connective tissue is a weird tissue type. It's very diverse. Muscles, there are different types of muscles, but hey, they're all muscles. They all seem pretty similar. Connective tissue is all over the place. So it's kind of a very broad grouping. I don't know why actually they put some of those things together. Nervous tissue, this one makes sense. Nervous tissue, it has to do with the nervous system, so it conducts impulses. So muscles are cells that contract. Nervous tissue, cells that send signals, that they have electrical signals. Well, it's chemical. It's a chemical electrical signal, and they form this network across your body. Obviously, you have big nervous system, very big brain. Maybe our Neanderthal didn't have such a big brain here, but here we'll give him a bigger brain. So bigger brain. He's smarter. But it's not just the brain. It goes down to the spinal cord, and coming off the spinal cord, you have spinal nerves. In between each vertebrae, you have nerves running out sideways. You have some nerves coming off your brain, like to your face and stuff, to your eyeballs, to your ears. Your brain is sitting in the dark. Your brain can't hear, it can't see, it can't touch, can't do anything. So then you have receptors all over your body, different kinds of receptors to give data to your brain to create a picture of what the world is. And all you have is an approximation of the world. You can't actually experience the world as it really is, but you can experience parts of it. And you might say, well, no, I'm experiencing reality right now. Well, no, you're not. You're experiencing a part of reality. Are you experiencing the radio waves passing through your body, the microwaves coming through the room, the light that is below, ultraviolet light or infrared beyond what you can detect with your eyeballs? No. Are you detecting sounds lower than the frequency that you can hear or higher than the frequency you can hear? No. They're there, but you have no perception of them. So you're only experiencing a portion of reality, only what you can perceive and interpret. Sometimes you can perceive something and yet you don't interpret it. So it doesn't make sense. So That's nervous tissue. Epithelial tissue, it covers things. Okay, so the skin is an obvious epithelial tissue, but linings too. You know, the inside of your cheeks, or the inside of your nose, or the inside of your urethra, or the inside of your bladder, or the outside of your bladder, even though it's inside your body, or the inside of your intestines, or the outside of your intestines. So, you know, here's a little bit of intestine, and the very outer layer is going to be connective tissue. The very inner layer, epithelial tissue, and the inner layer is going to be epithelial tissue. So it serves as a lining for everything. Okay. Organs. We talked about organs being groups of tissues working together, and it's some things we think of as organs, like, you know, the heart is an organ. True. Stomach organ. Yes. Intestines. Okay. The brain, but there are things that are less obvious that are organs. So my finger has multiple organs in it, because each bone, I have 3 bones here, each bone is actually considered an organ. And you think, wait a minute, isn't it just skeletal tissue? Isn't it just bone? No, it's not just bone. There's blood supply to it. There's nervous tissue in it. So because there are multiple tissue types, by definition, it's an organ. See that tooth? I shouldn't show my teeth. I don't have very nice teeth, but each tooth is an organ for the same reasons. You know, it has the bony tissue, but it has connective tissue with the ligaments attaching it to the socket, the tooth socket. It has nerves going into it, so it has nervous tissue. It has a blood supply. So the strict definition of organ is almost not helpful, because there are too many organs. So, I mean, it's fine to just stick with the major, more obvious organs, but each muscle is an organ. Each bone is an organ. And then we have organ systems. And it's mostly the system level that we teach. You know, we talk about, well, let's study the digestive system. Let's study the skeletal system. Let's study the epithelial system or integumentary system. And so we'll go through some of these systems just very quickly. It might take me a while, but it's considered quickly. Okay, so let's look at the integumentary system, the skin. We live on land. We need a waterproof coating so that we don't just shrivel up, right? If you were an amphibian and your skin was wet all the time, you'd need to keep it wet so that you wouldn't dry out. We can be totally dry because we have dead cells that are covering us. Now they're kind of like scales. They're not as good as scales for keeping us watertight, but all these cells in here, this upper layer, they're all dead. So when you look at somebody, you're looking at just a bunch of dead cells walking around. Right? The hair cells, those are all dead. The skin cells, they're all dead. You don't have to go very deep before you get this little layer of living cells. This very bottom layer is the cells that keep dividing and dividing. And so some of these that are dividing, they're not dead yet, but they're dying. They're dying, they're dying, they're dying. And they're dying because this is the last blood supply right here. You know, there's some blood supply, there's some blood supply. So this is the dermis, where the blood supply is. This is dermis. The epidermis has no blood supply. Only the very bottom layer is getting oxygen and nutrients. And so as the cells get pushed up, they start to die because they're too far away. And they just, as a last act of dying, they cement themselves together. They produce lots of keratin, which is a waterproofing protein, and kind of makes them tough and hard. And they just hold on together and die. And you're losing skin cells all the time. It accounts for a lot of the dust that accumulates in your house. Is just skin cells falling off all the time. Hair, it's similar. It's a product of the skin. And here is this epidermal layer. It goes down. Ooh, here's a oil gland, a sebaceous gland associated with the hair follicle. And down here are the dividing living cells right here. And so this part, these are all dead cells getting pushed. So with every single hair follicle, you have a little oil gland just to oil these dead hairs. Why do we do that? I don't know all the reasons. It's a little bit antibacterial. It conditions the skin, and humans are especially weird because we spend all this money on soaps to wash away the oils, and then our skin's too dry, so we spend all this money on lotions to put the oils back on that we just washed off. Also, mammals in general are very stinky, in the sense that mammals rely a lot on scent to communicate and to distinguish each other. So we're smelly too. We produce our, each person has their own unique scent, and again, we culturally just get rid of that or cover it up all the time. So communication, skin's involved in communication. How? Well, through your scent. If you're embarrassed, then your skin will communicate that. Or maybe if you're turned on, there's some changes in your skin to communicate that. Or you use your skin. I mean, the skin is what people see. And so your facial expressions, obviously you rely on the muscles beneath, but how you shape your skin and the faces you make, that's all part of communication. Our skin also has a bunch of sweat glands, and the sweat glands have a little tube coming up to the surface, and the sweat comes out, and you have a lot of sweat glands. And humans are probably the sweatiest of mammals. We're able to sweat more than most. I mean, a horse is good at sweating too, and maybe a pig, I don't know for sure, but humans may have more sweat glands per square inch than any other mammal. And there's an interesting book called Born to Run that looks at some of the anatomy of the human in terms of did we evolve as long distance runners. And one of the things they talk about is the number of sweat glands, that we're able to jog long distances without overheating because we can sweat effectively. That's the reason. I don't actually know if that's why we have so many sweat glands, but it's a great cooling system, and not all animals have that. Dogs have to just pant through their tongue. Some animals just have no sweat glands because it is a way to lose water, right? Okay. Skin is not very thick. The epidermis and dermis, it's just a very thin thing altogether. You see kids sticking pins into their skin sometimes, because they're kids. And so here's a pin sticking into the skin, and if they get it just in that upper layer, they don't bleed. So you don't bleed until you get down to the dermis. But you also realize how thin the epidermis is, because it doesn't take much of a scratch before you do start to bleed. Okay. Also, no nerve cells in this epidermal layer. So technically, if you really just are putting that pin only through the epidermis, it doesn't really hurt, because the nerve receptors are in the dermis. And we have different types of nerve receptors to detect different things, to detect hot and cold, light touch, deep touch. So different nerve endings for different things. Pain, we have pain receptors kind of all over. Okay, so a lot going on in the dermis. Below the dermis is fat tissue, and this adipose tissue or fat tissue, most mammals don't have a subdermal fat tissue. They just store fat only like around the intestines. So a gorilla, for example, you can feed it junk food all the time, and it really won't put on that much weight. It won't put weight onto its hips or its belly under the skin. It simply can't. Which mammals can put on a lot of weight under the skin? Aquatic mammals, like a whale or a seal or a walrus, those sorts of things. And so it's the aquatic ones, and that's, some people hypothesize that humans had an aquatic ancestor or a semi-aquatic ancestor. Elephants are another one where they can put on fat tissue, and a hippo. Now, a hippo's aquatic, an elephant's not aquatic, but an ancestor to the elephant was actually aquatic or mostly aquatic. So it's possible that we had an aquatic or semi-aquatic ancestor. That may also explain why we're hairless, because you think of mammals that live in the water, most of them are hairless. So maybe that's why we're the naked ape in terms of hair. Okay, moving on to skeletal system. By the way, one last thing about the skin, very important for protecting you against infection. It's a effective barrier. All these dead cells don't give the bacteria much to eat. You get bacteria on your skin all the time, but they don't thrive there, right? They don't start to grow and reproduce too effectively. But if you have a cut into your skin, and it doesn't need to be much, but a little bit of a scrape, then the bacteria sometimes start to get into the living tissues, and you get swelling and redness and a bit of an infection there. You also get bacteria down here. Even though the sebaceous gland is kind of antibiotic, some bacteria like to eat these secretions. They like to eat the sebum. So sometimes you'll get a bit of an infection here, and you'll get some pus buildup, which is dead bacteria and dead white blood cells, and it will seal off, and you'll get, what do you get? You'll get a pimple, right? You get a zit that's raised up there. So, but if you didn't have skin, you'd die of bacterial disease just very, very quickly, which is why burn patients need to be very careful putting special creams on them, and they're very susceptible to infection. Okay, skeletal system. We are vertebrates. We have internal hard bony skeleton. We have about 206 bones. I say it's about because sometimes bones are counted as 2 bones until they fuse together, then they're counted as 1 bone. And some people have more bones than others. You know, occasionally, instead of 5 lumbar vertebrae, somebody might have 6 lumbar vertebrae. But usually it's 206 total. And boy, how do I get so many bones? Well, look, 3 bones in each finger, plus 2 in the thumbs. So 3, 6, 9, 12, 13, 14. Here's another 14, that's 28. Look at my feet, and I've got the same number in my toes. So 28 times 2, there's 56 out of the 206. And that's not including the palms and the soles of the feet. You know, there are 5 there, 5 here, 8 in my wrist here, 8 in my wrist there, 7 in each ankle. So it's, you know, the most bones are in the hands and feet. Plus vertebrae, you got quite a few vertebrae, and ribs. You know, ribs, you got 12 ribs on each side. And even your skull, you have a bunch of bones fused together here, right? It's not just a skull. You have frontal bone, 2 temporal bones, occipital bone, you have maxillary bone, you have nasal bones, mandible, and quite a few others that, you know, little pieces, zygomatic bone on each side. Okay, why so many bones? Well, we attach muscles to bones, and any movement, we're actually pulling on bones with our muscles. Okay, we don't just, the skeleton can't move itself, and muscles, if they weren't attached to bones, they wouldn't really do anything. You do have, okay, right here, the pucker your lips. You can do that without any bones. Your orbicularis oris is just around, there's a puckered lip, extremely puckered lip. Orbicularis oris muscle is just around the skin of the lips there, and doesn't attach to bone. Or your eye, you can close your eyes without really attaching to bone. Okay, bones are important mineral deposits. The cells are surrounded by a calcium phosphate matrix. There's also, you know, so lots of calcium stored in your bones, magnesium stored in your bones, phosphorus stored in your bones. And these are important for the bones themselves but they're also needed everywhere else in your body. And potassium, not as much, but if let's look at calcium. If you don't have enough calcium in your diet, your body just automatically takes it out of the bone. It just starts breaking down the bone, and because you need a constant level of calcium in your blood. It's not a whole lot, but if you drop below, you can't contract your muscles, your nerves won't work. So you absolutely need to maintain blood calcium levels. You need it more than you need a strong skeleton. So your body doesn't hesitate to make withdrawals from the bank. So your bones are mineral bank. And if you're making a baby and nursing that baby, there's extra withdrawals being made. So you have to be careful to get enough calcium in your diet. Women are more prone to osteoporosis than men, largely because they make babies. And that baby, as lovable as they are, it's a little parasite in your body, and it's sucking off your resources, right? Everything it gets came from you, and if you didn't have that extra in your diet, it just sucks it out of your bones. Okay, some bones are hollow, filled with marrow. So here's a hollow bone. Gee, it looks like my hollow intestine, but so there's marrow, and in this marrow is where a lot of your red blood cell production takes place. So your blood is made inside of your bones, which is kind of interesting. Bones are alive. The cells do need nourishment and everything, and bones are changing all the time. If you want to strengthen your bones, make your bones thicker, then use your muscles more and weight-bearing exercises. Because what happens if you have a muscle that is attached right here with a tendon, and it pulls and pulls on this bone, that where it pulls, that bone's going to get thicker, and so the stress from weight-bearing exercises makes your bones thicker. Send an astronaut into space. If that astronaut doesn't do exercises, they'll come back. They will hardly even be able to walk. Their muscles will have atrophied. Their bones will have thinned down. You need to stress your bones if you want to keep them working well. Okay, gravity is helpful, but lifting weights even more helpful. Okay, looking at the skull really quickly, the cranium and the jaw. So if you just say everything that doesn't move is the cranium, and the lower jaw is your jaw, that's the only movable part of the skull right there, the temporomandibular joint between the temporal bone, which is here, there's the temporal bone, and the mandible, which is here. So the temporomandibular joint, you just have a little joint up in here. That's the only movable part of the skull. You have many other bones, and usually you have cranial bones and facial bones. That's kind of how they distinguish. Cranial bones being bones that have contact with the cavity where the brain is. So you have frontal bones and temporal bones and parietal bones, occipital bones, and ethmoid bone, like this one here, actually goes up and touches into the cranial cavity a little bit. And then your facial bones, like your nasal bones and your lacrimal bones that has the tear duct, the zygomatic bone here, which is your cheek. The other part of your cheek is the maxilla, and that comes down and holds your teeth, your upper jaw. And some interesting things, you see little passageways here and there for nerves and blood vessels. You have little bones inside your nose. These are covered with tissue, mucous membranes and stuff, but you have little shell-shaped nasal conchae inside your nose. Yeah, fun. And you have landmarks. So this bump behind your ear, feel behind your ear, there's a definite bump there. That's called the mastoid process. It's part of the temporal bone, but it's given its own name because it's a landmark. And there are lots of landmarks if you like to learn anatomy. Okay, your skull, the main job, it's protecting the brain, right? It's a crash helmet. Not good enough for a motorcycle, but it helps for walking into walls at least. Your brain is like, jello or custard. It's not very solid. It can easily get squished. Okay, vertebrae, protecting the spinal cord is the main job, plus allowing for movement. So we have 7 cervical vertebrae, one that the skull is attached to, the atlas or C1, and then an interesting 7 cervical vertebrae is a mammal trait. All mammals have 7 cervical vertebrae. Let me get a phone call here. Real quick here. Hello, this is Kevin. Okay. Sorry about that. Let me see if I can get this going again. I'm not sure if I've got the right... Boy, I hope it's fitting the whole thing. Alright, moving along. I realized that we got a bunch of slides that I should talk faster and say less about each slide. And how can I hide this thing? Go away. Okay, I'm back to recording not full screen and not drawing on the screen because I'm having some technical problems again. Okay, moving along. So, talked about the spinal cord. I was going to say every mammal pretty much has 7 cervical vertebrae. It's a mammal thing to have 7 cervical vertebrae. 12 in the thoracic. That varies by mammals and by different vertebrates. 5 in our lumbar, and basically 4 or 5 fused together in the sacrum, and then the coccyx, the tailbone, is a few of them fused together. Okay. Ribs attached to the thoracic vertebrae. By definition, that is a thoracic vertebrae. It has a rib attached to it. So there are 12 ribs. The last 2 do not come around and attach to the sternum at all. They're just floating ribs. Some people who feel like their waist should be even skinnier will have these floating ribs surgically removed. Just one of those weird human things. 5 false ribs, meaning that they're still ribs. I don't know why they call them false ribs, but ribs 8, 9, and 10, they don't have their own cartilage connection to the sternum. See how they join up with the cartilage from rib number 7. So for some reason, 8, 9, and 10 are considered false, and 11 and 12 are also considered false. I don't like that term. They're still just ribs. So, but 7 are considered true ribs because they're attached to the spinal cord and attached to the sternum with cartilage. 8, 9, 10, 11, 12 are false. 11 and 12 are also floating. Why do we have them? Protection. Right? Protect the heart, protect the lungs, protect the liver and the spleen. The lungs don't come down all the way. The liver occupies a lot of the space here. So on your right side, on the left side, you got the spleen. Your kidneys are also protected partly by these floating ribs, and this is why kidney punch is not allowed in boxing, because since these are floating ribs, you could potentially push them in to stab a kidney by punching there. Okay. Arms and legs held on to the axis of the axial skeleton. We have now appendicular, the appendages hanging on. So we have the clavicle or collarbone, clavicle, and the scapula or the shoulder blade helping hold the humerus, the arm bone there. Okay, so that's all part of it. Let's see if we can close that. Anyway, so we have a pectoral girdle and a pelvic girdle. Pelvic girdle holding the legs on, pectoral girdle holding the arms on. And we have ball and socket joints for both. Ball and socket joint attaching the humerus to the scapula, ball and socket joint attaching the femur to the pelvis. And this acetabulum is actually 3 bones hooked up together here. Okay. Anytime bones are meeting other bones, it is a joint. And not all joints are movable. So even though I can't move the separate bones of my skull, they're fused together. That place where they're fused together, the suture is considered a joint. It's a fibrous joint. It's immovable, but it's still a joint. Most of the joints, they're movable, and that's the ones we think about most. So a ball and socket joint is the most movable joint in the body, and where the humerus joins the clavicle, that's a pretty shallow ball and socket joint, and this is the most movable joint in your body, the most movable. And because it's the most movable, it's also not as stable as it could be. There's always a trade-off, stability versus mobility. Other types of joints, pivot joints, where the radius pivots against the ulna. So to open a doorknob or whatever, you twist. It's this twisting motion is a pivot joint. Your neck has pivot joints. Your wrists can pivot a little bit. Your ankle. Hinge joints is kind of more your typical. All your fingers have hinge joints. Your elbow is a hinge joint. Your knee is a hinge joint. Ligament is attaching bone to bone, and the knee has several ligaments to hold it together, and it prevents too much movement and keeps things held together properly. Now, you have tendons of muscles that also help hold everything in place, but the ligaments are necessary. And with knees, you hear people getting knee surgery. It's usually the ACL that you hear about, the anterior cruciate ligament. It's called cruciate, meaning cross, because these two ligaments cross each other. So there's a posterior cruciate ligament that touches the femur in the back and comes forward onto the tibia, and the anterior cruciate ligament. Did I get that wrong? I think the anterior is because it's anterior on the tibia. Yeah, that's what it is. So posterior cruciate ligament is posterior on the tibia. Anyway, the ACL is tight when you're standing straight. And so usually people injure it because they're standing straight or the leg is stretched out and maybe it gets hit from the side. And so that will tear the anterior cruciate ligament. It might tear some of the collateral ligaments as well. Might tear a meniscus that's sitting on the bottom of the knee joint there. So anyway, that's the most common knee surgery. Maybe some of you have had that kind of knee surgery. Okay, moving along. Voluntary versus involuntary muscles. Can you move it by yourself? It's voluntary. It's a skeletal muscle. Can you not move it by yourself? Can you control the movement of your intestines? No, you cannot. Can you control the movement of your heart? No, you cannot. So it's involuntary. So smooth muscle, cardiac muscle are not under your voluntary control. You cannot contract your uterus on demand. If you look under a microscope, you can identify 3 muscle types. The skeletal muscle type, nice even bands together. And here, look, multiple nuclei. I told you that one cell had multiple nuclei. This is a cell here. This is a cell here. The nuclei for muscle cells are just right at the edge of the cells. But this nice banding pattern will tell you that it's skeletal muscle. Nice smooth banding pattern. Smooth muscle, the cells are not nearly as organized, and they don't have any banding along them. So this would be your uterus, your small intestine, your large intestine. Your bladder has that kind of muscle in it. The heart muscle tissue, it looks kind of similar to skeletal muscle tissue. It does have some banding to it, but it has these little dark lines to join cell to cell. This is kind of interesting. With skeletal muscles, each cell needs to be stimulated independently by a nervous impulse. So if I'm picking up something not very heavy, I don't have to engage too many of my muscle cells. So I just send a little bit of nervous signal. If it's something much heavier, and I'm engaging more muscle cells, I have to send more nervous impulse. With the heart, the cells are all connected electrically. So when one gets the signal, it spreads to all of them, and they are all going to contract as a group. Now, not all of them at once. Because there's a bit of a delay built in, which we won't go into great detail here. Muscles can only pull. Okay, they can only shorten. They can't push. Now you can push, but you're shortening a muscle as you push. You're always shortening a muscle. You're contracting a muscle, making it shorter. So muscles are often arranged in antagonistic pairs, meaning that they work opposite of each other. There are also lots of muscles that work synergistically. They work together. So your biceps is not the only muscle to bend your elbow joint. There's also a muscle beneath the biceps that does the same job, same exact job, but it's a different muscle. So those are synergistic. But the biceps and triceps are antagonistic. They do opposite. And so your quadriceps and your hamstrings, those are opposites. Your heart is a double pump. It's special, for moving blood through all the vessels. It's a double pump because the right side and the left side go to different places. Blood comes from your body, deoxygenated, into the right side of your heart. It gets pressurized and sent out to the lungs. And then it comes back from the lungs, and now it's got lots of oxygen, but it comes into the left side of your heart. And it gets pressurized again and sent to the body. So right side pumps to the heart, left side pumps to the body. So it's a double pump. Now, in action, the top contracts and then the bottom contracts. But functionally, it's right side, left side for what the double pump is. Okay, your blood travels through these pipes all over your body, and you have big tubes initially, and they get smaller and smaller and smaller until, it's like going from the highway onto a main road, onto a smaller road, into your driveway. It gets smaller and smaller, and the blood vessels get very, very small. It's more like going to the sidewalk or whatever, or a little footpath. All exchanges happen at the very smallest blood vessels. So any exchanges of nutrients or oxygen or wastes or anything like that happens only in the capillaries. I was going to walk you through the heart. I think I can only draw on here if I go to full screen. And if I go to full screen, I don't know if you'll see it anymore. Let me see if I can get it full screen. The program is being really weird today. Come on. Just let me do a slideshow. Okay, slideshow go. That's not how I usually go to it, so from current slide. We're gonna try. I don't know how well this is gonna work, but the heart is kind of heart-shaped if you don't include all the vessels that come out of it. And it's divided into two. If you look at it internally, there's a wall, a septum, and this is the right side over here. This is the left side because we're looking down at a patient, so to speak. The blood from the body is coming into the right side through a superior and inferior vena cava. So we have vena cava, they're blood vessels returning blood to the heart, and this blood is oxygen poor, and it goes through a tricuspid valve. It's got three little flaps there, into the right ventricle. So this is the right atrium where the blood is received. It goes into the right ventricle and it exits the right ventricle. I'm going to draw the exit door there. It's actually a little higher up. This is an approximate shape. We'll look at a picture that's maybe a little better. But it leaves, but it came through the tricuspid valve, or the right atrioventricular valve, to go from atrium to ventricle. Out of the right ventricle, it goes through the pulmonary semilunar valve. Semilunar because it kind of looks moon-shaped. It goes through the pulmonary semilunar valve. It's on its way to the lungs. When it's coming back from the lungs, it's going to enter actually through 4 vessels into the left atrium. And on the left side, the valve between the atrium and the ventricle, the left atrioventricular valve, is called the mitral valve or the bicuspid valve. So on the right we had tricuspid, tri-right because it had 3. Left we have bicuspid, just 2. It's called the mitral valve because if you look at it upside down, it kind of looks like the Pope's mitre hat. Kind of. That's how somebody thought. So that's why it's the mitral valve. Anyway, into the left ventricle. Now the left ventricle is the strongest of the heart chambers because it's got to pump to the whole body, so it's got to really pressurize things. I'm going to draw the exit right here, the aortic semilunar valve. Technically, the valve is actually clear up here. There's more of a tube that sneaks up like that, and it's going to go out the atrium to the whole body, and the atrium's, or out the aorta, not the atrium, the aorta. The aorta is even a little thicker than that, and it goes down behind the heart and down towards the body, and there are vessels coming off towards the arms and towards the head. Okay, so the aorta is the big valve, the big vessel supplying blood to the whole body. And this aortic semilunar valve, very important. Anyway, so blood to there. So right side pumping to the lungs, left side receiving from the lungs, pumping to the body. And there are 4 valves. When you listen to a heartbeat, you are listening to the valves slamming shut. So the 2 atria contract at the same time. So blood is forced from the atria into the ventricles, and then the 2 ventricles contract at the same time. When the ventricles contract, the ventricles contracting slam shut the atrioventricular valves because the blood tries to go backwards, and these valves just they just shut tight. Okay, and this door and this door are open when the ventricles are contracting, right? Because they're forcing blood out to the lungs, out to the body. When the ventricles relax, the blood kind of tries to go back because it's under pressure, and it slams shut the valves, the semilunar valves, the aortic semilunar valve and the pulmonary semilunar valve. And so those are the sounds you hear. The first sound is the AV valve slamming shut. The second sound is the semilunar valves slamming shut. Okay. Okay. Moving along. Arteries are carrying blood away from the heart, and so there are pulmonary arteries that carry deoxygenated blood because they're on their way to the lungs from the heart. So it doesn't matter that they are deoxygenated. What matters is that they're going away from the heart. Veins are coming back towards the heart, and it doesn't matter. It could be clear down into your toe. If it's going towards the heart, if the blood is on its way back, it's in a vein. Capillaries are between the arteries and veins, and you don't go big artery, big vein, with capillaries in between. You go big artery to smaller arteries to even smaller arteries to little teeny arterioles that are the size of a thread, and then capillaries. And the other size of that, then the other side of those capillaries, you have a thread that is the smallest venule that becomes a small vein, and bigger veins and bigger veins. So capillaries are microscopically thin, and you have thousands of miles of capillaries all through your body. You need to get the blood pretty close to every cell for it to get the oxygen it needs and get rid of the waste products and everything. There's a better picture of the heart. Vena cava, superior vena cava, inferior vena cava, returning blood from the body into the right atrium. There's the tricuspid valve, or the right atrioventricular valve, into the right ventricle. It's going to leave towards the lungs, in the pulmonary. There's the pulmonary semilunar valve. This is a pulmonary artery. These are pulmonary arteries going to the lungs. These are pulmonary veins. They're oxygenated because they're coming back from the lungs, but they are veins because they're coming back to the heart. And so pulmonary veins entering the left atrium go through the bicuspid valve into the left ventricle and out the aortic semilunar valve. There's the aorta, the largest blood vessel of the body, and you can see some things coming off of it towards the head and neck and shoulders. So know the basic flow of blood through the body, and it goes around and around. It takes about a minute for it to go around, and it does this day and night all the time. Most of the blood at any one time is sitting in your veins. You have more blood in your veins than in your arteries because your veins, the pressure has been lost, right? You don't have the blood pressure to get it back to the heart, so it's coming along pretty slowly. So there's kind of a buildup in your veins. It's maybe 60% of the blood in the veins and 40% in the arteries. As you exercise, your muscles will squish your veins and push more of that blood into circulation, and it will become more 50-50. If you're sitting on a plane or something for a long time and your legs aren't moving, you tend to get swollen ankles, and just sitting a lot, the blood tends to pool in your legs, and you're more likely to get varicose veins because the veins have little one-way valves on them that will fail if you're not moving your legs and getting that blood moving occasionally. Some people have varicose veins regardless of what they do. It's not a matter of sitting a lot. Some people are just more prone to it. Okay, blood. You take blood and you spin it in a centrifuge, and you'll separate the red blood cells from the plasma. The plasma has mostly water, but it has various hormones and different proteins dissolved in it, like your antibodies and your fibrinogen that's going to be involved in blood clotting, your albumin, which is the same protein that you find in egg white, which is why plasma looks a little bit like egg white. Anyway, and they'll measure what percentage of your blood is red blood cells. That's your hematocrit. And women tend to have a little lower hematocrit or red blood cell count compared to men. And if you live at low altitudes, you won't have as many red blood cells as if you live at high altitude, because the red blood cells carry the oxygen. The red blood cells, this is under an electron microscope. Here's a white blood cell and a red blood cells. These guys carry the oxygen and the carbon dioxide. They're carrying the waste products as well. And they're packed full of hemoglobin. And hemoglobin is a molecule that carries the oxygen. And they have tens of thousands of hemoglobin molecules packed into one blood cell. And you can see they're kind of shaped like a jelly donut that lost some of its jelly. The nucleus has been taken out. The mitochondria have been taken out. A lot of their organelles, the cell organelles, have been taken out. So it's just a transport vessel. It's still alive, but it's lost most of its machinery. And an interesting thing is that red blood cells are the one type of cell in your body that cannot use oxygen, since they have all their machinery taken out. They still have a way to get some ATP, but it's just ironic that they are carrying oxygen. Here's this cell full of oxygen, but it doesn't have the machinery to use oxygen. Your white blood cells are going to be involved in your immune system, fighting off the bad guys, right? And most of the white blood cells, the most common type of white blood cell, it only has a lifespan of about 4 days because they're always picking fights and you're always getting invaded by bacteria and viruses and things. And these guys are going out to battle, and they're just, it's kind of like they start throwing grenades right next to themselves. And so they start putting out chemicals to destroy the bacteria, but they're blowing up these chemical bombs right next to themselves, and they die in the process. So good job, white blood cells, sacrificing yourself for us. And you know, when you get sick, the options are your immune system wins or you die. Those are your two options. So you know that you have a pretty impressive immune system because most of the time you win. You know, sometimes you're sick for several days, but almost always your immune system gets the upper hand. Okay, platelets are just little broken up fragments that are going to help in blood clotting, along with that fibrinogen, that dissolved protein. Blood clotting is actually a fairly complex process. We're not going to go into it, but platelets are part of the blood clotting. Lymphatic system is involved in immunity. There are lots of white blood cells in your lymphatic system. It's also because every time you go through a capillary bed, you lose a little bit of fluid. And so every time your blood circulates, a little bit of the plasma leaks out in the capillaries. Because the capillaries are fairly open. That's where the exchanges are taking place. So you would just start to swell more and more and more if you didn't have a lymph system, the lymphatic system. So it basically is picking up that extra fluid and dumping it back into the blood. That's one of the jobs of the lymphatic system. Pretty big job. So if a woman's had a radical mastectomy and they took out a bunch of lymph nodes, she's going to be really prone to edema in her arm, where they took out the lymph nodes in the armpit, because she doesn't have the system's been broken for returning that extra fluid back into the bloodstream. So she has to be a little more careful. Okay, respiratory system. This is breathing. Gas exchange in the lungs. Getting rid of carbon dioxide, picking up oxygen. That's the critical stuff. It's actually more critical to get rid of carbon dioxide. That's what triggers your desire to breathe. If you just hold your breath for as long as you can, your absolute need to breathe is because your body senses carbon dioxide building up. It's not because it senses you're running out of oxygen. You actually don't sense very well that you're running out of oxygen, but you sense very quickly if you're building up CO2 levels. Most of the respiratory system is just, moving the air in and out. The nasal cavity, the trachea, the bronchi, and so forth. It's just moving in and out, in and out. Again, gas exchange, there has to be a capillary, it has to be a microscopic level, so we go into the lungs, deep, 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 and we'll find alveoli. And these are little tiny clusters. They're microscopic, little grape-like clusters covered in microscopic capillaries. And the capillaries, this is, deoxygenated blood slowly coming from the heart. This has been pumped from the right ventricle, this tiny little arteriole, and then the capillary bed right over the alveolus. And then it forms a little venule on its way back to the heart, back towards the left atrium. So alveoli are the gas exchange places. These get messed up with smoking, long-term smoking. You get emphysema, where several alveoli, they lose a lot of the structure. And so you just have big pockets instead of these tiny little microscopic ones, and gas exchange gets messed up in emphysema. Digestive system, because we eat, because we're animals. Chew, 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 swallow, down the esophagus, into the stomach, churn, 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 mix with acid, kill all the bacteria that you just ate. Go into the small intestines, add bile from the gallbladder that was made in the liver, add a bunch of digestive enzymes that were made in the pancreas into the small intestine, chemically break down the food into smaller and smaller molecules until in the small intestine you're able to just absorb absorb it right into the bloodstream. Again, there are going to be capillaries, lots of capillaries in your intestine for absorbing that food. What doesn't get absorbed goes into the large intestine, where now the bacteria are really happy that live there because you're just giving them food. The bacteria give back a little bit. You know, some of your B vitamins and stuff and your vitamin K come from the bacteria living in your large intestine. But large intestine is mostly pull out a lot of the fluids, recover a little bit of what you can, form feces, and then out it goes, right, down to the rectum and out the anus. Okay, have to hurry to finish up here because I've got a review session coming up. The brain has different lobes. It's a little bit arbitrary, but you have a left and right hemisphere. That's not too arbitrary, but the lobes, there's a frontal lobe, parietal lobe, temporal lobe, occipital lobe, different functions in each. Most of what you think of as you know, your personality and your conscious thoughts, that's frontal lobe. Processing what you hear is temporal lobe. Processing what you see is occipital lobe. Forming words is parietal lobe, probably. But most of your conscious thought and your personality is frontal lobe. Your cerebellum is coordinating your muscle movements, letting you walk, letting you run and jump and do ballet or whatever. The spinal cord is sending messages back and forth between the brain and the body. And so you have a little brain stem here where you're controlling things like heart rate and your breathing rate and keeping you alive and making you hungry or thirsty. You know, basic survival stuff happening with the brain stem. And then again, spinal cord is a highway of nerves going back and forth between the brain and the rest of the body. Because, you know, just if you're quadriplegic, then that highway's been broken. And you can still think, but you can't control your body. Okay, and moving along, senses. This is the kind of scary picture of an eye. A pupil is just an opening. You know, it's black because there's no light on inside your eyeball, but it's just an opening. The iris is just a muscle that controls the size of that opening to adjust how much light is getting to the back of the eyeball. It's on the back of the eyeball where you have the nerve receptors that pick up the light and form the image. So the iris can contract in and out to contract or relax to determine the size of the opening. And we pay attention to the iris because it has cool colors in it. It doesn't need the colors for anything. It's just a little nifty thing that we like as humans. But the sclera is the white of the eye, and you can't see it from that angle, but you know, here it's sclera, then iris, and then we have a cornea, which is totally clear, that goes over the top here. So the iris, again, the pupil is just the opening here, and the light goes through a lens that's clear, and the lens focuses it onto the back of the eyeball, and it's back here in your retina where you have all the cells to respond to the different wavelengths of light. So the light that passes straight focuses right here. If the cornea isn't shaped quite right, the whole eyeball is not shaped quite right, then the focal point, the sharpest focus, might be right here, or it might be right here. It might be someplace besides the retina itself. In that case, you may need corrective lenses. You might be short-sighted or nearsighted. Have some muscles to control the iris, and also to control, you have muscles that control the lens for, you know, focusing near or focusing far. And at the back of the eye here, here's the entrance of the optic nerve, and the optic nerve spreads out. And there's one, like I said, one spot in particular that has a high number of nerve endings, because your sharpest focus is the light that comes in directly to that one spot, that fovea capitis. And you think the whole world is in focus, but if you look at a page, you can't read everything on that page all at once. You have to be moving your eye all the time, because the only thing that's in sharp focus is what you're looking at directly, the light waves that are entering straight on. everything else, you don't have nearly as many receptors, and your brain kind of keeps a mental image of everything, and it gives you the impression that the world is in focus, but you only have a very small point of your world that's in focus. Everything else is out of focus, and it's just a trick of your brain that and your eyes moving about and capturing that data to think that your world is in focus. Hearing, again, it's a little bit of a misperception. You know, we think we hear the world really well, and we do. We hear it better than what it is. We amplify the sounds. So here's this collector device, this pinna, this ear, and it funnels the sounds into an eardrum or tympanic membrane. We have these three little bones, malleus, incus, and stapes, three little middle ear bones, which I think I mentioned in a reptile, these are part of the jaw. In mammals, they've moved up to here, and they mechanically amplify the sound. So they are attached to the tympanic membrane on one side and to a little teeny membrane called the oval window on the other side, and the vibrations, as they get transmitted, it amplifies the signal about 20 times. So this is, your sense of hearing is actually your most sensitive sense. The amount of signal that's coming in from a whisper is minute. Your tympanic membrane, your eardrum, is vibrating less than the width of an atom, and yet you're able to pick up that sound. And so this is very, very sensitive. It's also the sense where you can go from, you know, the lowest amount of sound that you can hear to the highest amount at which it's painful. That's a millions of fold difference. So compared to light, you know, the very smallest amount of light you can detect up until the brightest light to where everything's washed out and it's painful, that's a much smaller range. Or the lightest touch that you can feel until the hardest touch at which, you know, it's too painful or it's crushing you or whatever, that's a much narrower range than with hearing. So hearing gives not only, it's the most sensitive, and it has the biggest range. You can stand you can pick up the small signal, and you can withstand the largest signal with your hearing. So that's kind of cool. The hearing, well, there are little hair cells in the inner ear, in the cochlea, and then they transmit signals on the auditory nerve into the brain, and the brain interprets what those signals mean. And you know, different frequencies stimulate hair cells in different parts of the cochlea. You have also in this inner ear 3 semicircular canals. They're involved with your sense of gravity and motion and your sense of balance. And we're not going to go into how they work in the interest of time. Sense of taste, this is chemical detection. Sense of smell is also chemical detection. They work together, mainly related to your food. So sense of smell, here's this olfactory bulb with little nerves coming down into your nasal cavity. You can see it's pretty high up in your nose, so you might sniff to get air molecules up to those receptors. A lot of your sense of taste is based on your perceptions from smelling and even from seeing the food. If it looks gross, it's harder to see that it tastes good. This little map of the tongue is not actually too accurate. It's not. Nowadays we say it's not really like this. You can detect these tastes all over your tongue, and it's not just bitter, sour, salty, sweet. There's also umami, which is kind of a meaty taste to it. It's a amino acid that you can pick up on. So umami is another class of taste. And fat, you do have receptors for fat, and just tasting fat. You know, things taste better if there's butter or cream or whatever. You know, your body says, give me more of that. So there might be questions about this kind of map of the tongue and tasting sweet here. And so I don't know if there are questions, but it's not really too accurate, to be honest. Okay, and sense of touch, we've mentioned this already, that your touch receptors are down in the dermis, and you have different receptors for light touch, heavier touch, pain, hot and cold. story of a girl who had no pain receptors. She was just born with no pain receptors. You think, oh, that'd be nice to not feel pain. It's not a good thing. As a kid, she would chew on her tongue like it was bubble gum, and she was like mashing her tongue, like eating her tongue, literally. They had to pull out her teeth to keep her from destroying her tongue. Just at night once in her crib, she ripped out one of her eyes. She just playing with her eyeball and squishing it. And so she didn't totally rip it out, but she made herself blind in that eye. And so they had to like put a protective goggle over her other eye and just try to keep her fingers off of it. And and then as she's growing up and she's learning to cook, and she drops the fork in the spaghetti, boiling pot of spaghetti, she just reaches in and grabs it, not realizing she's burning her skin. So pain can be a good thing to tell you what not to do. Okay, we're gonna stop there, and I'll see if I get to see some people and